So, good evening, everyone. Welcome to the 11th live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRS scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So, in today's session, we'll first revisit the last live session that was for week 10 content in a quick recap manner, and then we'll look into the things that are covered in the week 11 content. So the content that we will discuss today is divided into four sections. First, we'll have an overview of corrosion. Then we'll talk about carbonation induced corrosion and chloride induced corrosion. And then we'll talk about science behind corrosion, mainly in terms of thermodynamics. And finally, we'll conclude the session. So in between, we will have some objective questions, like around 18 questions in total, that will challenge your understanding about the concept. And finally, I will address any other queries post discussion. So in the last session, we started discussion about durability of concrete, where we first talked about what does durability mean by defining it as per ACI standard and as per IS provision. We understood what how durability of concrete is affected by two factors: the concrete system and the aggressiveness of the environment, where the concrete system governs the concrete quality while the environment defines the rate of degradation or deterioration of concrete. In IS code definition, we understood that degradation influences the service life of a reinforced concrete structure. So we understood this again by looking at a performance versus time ideology, where we understood like how performance degrades over time, which leads to end of service life, and then how repair, retrofitting, and rehabilitation can improve the service life. Going one step further, we understood what each of these three R's, that is repair, retrofitting, and rehabilitation, means in terms of their role for enhancing the durability of concrete. And then coming back to the course content, we define different ways in which degradation can happen in a concrete structure, uh, which we which can be classified into six divisions: mechanical, physical, structural, chemical, biological, and corrosion. In this, we talked in detail about chemical degradation, where we discussed about sulfate attack, both internal and external, along with delayed adringite formation. We talked about acid attack, we talked about alkali aggregate reaction, and we also discussed about phase thaw action. And we saw what are the remedial measures for each of these attack. So this was the content that we covered till in the last session. My screen should be visible. Is my screen visible to everyone? Hello, Shreyash? Yeah, it is visible since the start. So it might be due to some network issues at your end, maybe, because today my network won't be a problem. Okay, whenever there is a screen issue or something which is not visible to you and I have discussed, just unmute and speak or try it in the chat box. So I will revisit that slide again. Okay. It should be visible today. There should be no network issue. Okay, so now the next topic that we'll discuss today and in the next session also will be concrete degradation due to corrosion. Okay, so most of the concrete degradation, like or maybe over 90% of the issues in practical application, they arise due to corrosion of embedded steel reinforcement. And to support this statement, I have shown on this slide few facts about some international organization and how they have related cost incurred due to corrosion damage repair to the GDP of the country. So there is a NACE impact report of 2024. NACE is a National Association of Corrosion Engineers group. So according to their report of 2024, 2014, they have said that the cost of corrosion repair damage is estimated to be around $2.5 trillion per year, which contributes up to 3.4% of global GDP. The same report in 2016 also said that 50% of the structure which shows major repair requirement within their first 10 years of life is due to corrosion. And similarly, there is a report by IZA, the International Zinc Association, which has said that the corrosion repair damage cost can aggregate further in developing countries like India, where it contributes up to 7% of the GDP. So these numbers shows that how severe a issue corrosion is for a infrastructure development. Now we know that corrosion is a highly sensitive topic for reinforced concrete. But now what is corrosion? So I would like you I would like to present you one of the simplest way to define corrosion. Okay. So if you are able to understand and remember this definition properly, everything that we'll discuss in the next two sessions will be easier to understand. Okay, so the definition of corrosion can be broken down into three key points, and understanding these three key points is enough to understand corrosion. Okay, so how are these 3 points framed? So corrosion is a Omkar, just mute yourself. Okay, so first is corrosion is a natural phenomena. Okay, which is based on interaction of metal with its surrounding that leads to loss of functionality of steel and subsequent structural collapse. Okay, so these three are different parts of the definition in which we define corrosion. So now the first point of the definition, that is corrosion is a natural phenomena, is related to thermodynamics of corrosion, that defines the possibility of corrosion of something to occur or not. Okay, thermodynamics, it defines the possibility of something whether it will occur or not. Okay, second point, that is interaction of metal with its surrounding, it defines the kinetics of the reaction, at what rate the corrosion reaction will occur. And the third point, that is loss of functionality of steel and subsequent structural collapse, it defines the result of corrosion action. Okay, what is the effect of corrosion? So from first two points, we are understanding the cause of corrosion, and the last point gives us the effect of corrosion. Okay, so during the content ahead, we'll talk about all these 3 points separately so that we are clear with the definition. So, if we see the thermodynamics of corrosion, so what thermodynamics says, every material which is stable, every material is stable in its lowest energy state. Okay, this is a universal law of nature. Now, when we make steel, okay, from iron ore, we have iron ores like hematite, magnetite. Okay, so these iron ores, they are processed in industry in furnaces to make steel. So when we make steel from iron ore, we impart energy to the system. Okay, so naturally the reinforcements that we have, they are at a higher energy level because they has been processed from iron ore. Okay, now my steel, it is at a higher energy level compared to natural ore. So this steel will try to convert back to its ore form, which is at a lower energy level. And that's the reason why we see corrosion is a natural phenomena. It will occur, we can't prevent it, because it is a universal law of nature that every material wants is stable in its lowest energy state. So steel will also try to convert into its lowest energy state, okay, which is in the form of ores. Okay, now this says that corrosion is bound to happen, but the question is at what rate. So the rate of corrosion is defined by the kinetics. Okay, so simply saying, corrosion is not just one reaction. Okay, it is a electrochemical reaction which is made of two parts, oxidation reaction and reduction reaction. Okay, so oxidation is conversion of iron into iron oxide, which releases electron, and reduction is consumption of this released electron by oxygen in the presence of moisture to form a OH minus ion. Okay, so That's why we had the second point in the definition. It is the interaction of metal with its surrounding. Okay, so here metal is the anodic reaction which is oxidizing, and surrounding is my oxygen and water which is reducing. Okay, so it is the interaction of metal with the surrounding. The same you can see in the figure also. This is my iron, this is my steel reinforcement. Okay, so here you see Fe is converting into Fe2 plus. Okay, and it is releasing some electrons here. And oxygen, it is coming from the environment in the presence of water. It is consuming these electrons and converting into OH minus ions. And then this Fe2 plus and OH minus ions, they combine to form ferrous hydroxides and oxides, which is the rust that we see finally on the surface of steel. Okay, so this defines the kinetics of reaction, how fast these two reactions are occurring. That will define the rate of corrosion reaction. Now, when we talk about reinforced concrete, so this was when steel is directly exposed to environment. But when we talk about reinforced concrete, the pore solution of concrete, we know it is rich in alkali ions like NaOH, KOH, and calcium hydroxide. So due to this, the pH inside concrete, as we know, it is always greater than 12. Okay. Now, under this highly alkaline say environment inside concrete, the steel rebar, when they are exposed to oxidation, they form a protective layer which is known as passive layer. So you see there, this is concrete, this is steel which is embedded inside concrete. So under this highly alkaline pH environment, what happens? There is a protective passivation that is developed over the steel rebar. Okay, now what happens? This is a protective film. Okay, it will block the interaction of oxygen or moisture with the steel. Okay, so it act as a barrier against corrosion. That's why we say reinforced concrete is a compatible material. Okay, concrete, it needs reinforcement for its tensile capacity, and these steel reinforcement, it needs concrete to protect it against corrosion. Okay, and this is how concrete protects steel against corrosion. Okay, the passive film, it shields steel from further corrosion by acting as a barrier. Okay, so passivation, it helps us to reduce the rate of corrosion to a very low value. Okay, this is a passive layer, although oxygen and water can permeate through the passive layer, but the rate at which corrosion will be occurring will be very slow, which makes concrete to have an infinitely long lifespan. Okay, but in reality, due to ingress of aggressive ions from the surrounding atmosphere, like CO2 and chlorides, what they do, they break this passive layer over time. And once the passive layer is broken, oxygen and moisture can easily interact with steel and it can corrode the steel. Okay, so aggressive ions which are responsible for breaking the passive layer are no are CO2 and chlorides. Okay, so that's why we have two forms of corrosion: carbonation induced corrosion and chloride induced corrosion. Now, the third part of the definition is what's the end result of corrosion, and that is the corrosion product, or what we say as rust. So this rust can have different composition. So we saw one composition is ferrous hydroxide. So based on the availability of oxygen and moisture, there can be different forms of rust product that can form. It can be iron 2 hydroxide, it can be magnetite, it can be hematite, it can be iron 3 hydroxide, it can be ferrihydrite, it can be goethite. Okay, so there can be different forms of rust product which can form depending upon the availability of oxygen and moisture. Okay, and all these rust product, they have a they are expansive in nature. Okay, so like iron hydroxide, it occupies 3.7 times the volume of iron. Similarly, iron 3 hydroxide, it occupies 4.2 times the volume of iron. Okay, so on an average, rust occupies 4 to 6 times more volume than steel. Okay, now inside concrete, we know there is very confined space. Okay, reinforcement concrete, it is very tightly packed. Okay, so such expansive rust formation, when it occurs inside concrete, it gives rise to tensile stresses at the interface. Okay, and these stresses, if it exceeds the tensile strength of concrete, cracking will happen. Okay, and that is the end result of corrosion. The same you can see through these images also, like here you can see these are corroded stirrups. This is the main reinforcement got corroded, and due to corrosion, the cover concrete, it got delaminated. Similarly, here also you can see delamination of cover concrete happened due to corrosion of embedded reinforcement. The same thing has happened here, and the same, and this is a steel structure where you can see severe corrosion damage occurring everywhere. Okay, so on in this image you can see this is spalling of cover concrete, and this is delamination of the corner concrete piece that has been broken off due to corrosion of embedded reinforcement. Now, when we look this damage part due to corrosion on a time scale, like over time how it develops. So initially, until the corrosion starts, okay, so this time will depend upon the ingress of aggressive ions. Okay, so I have this concrete, okay, and I have this rebar at this position. Okay, there is some cover, say 50 mm. Okay, now my steel is in passive state, so it is not corroding initially. Degree of corrosion is very small or negligible. Okay, and there are chloride ions, suppose they are, which are present in the atmosphere. Now until these chlorides ion will reach the steel surface, we can say that corrosion won't initiate. So this step 1, this step is known as the corrosion initiation. How much time it takes for corrosion to initiate. Okay, and it depends upon the ingress of aggressive ions through the cover concrete. Okay, how slow concrete can make those aggressive ions reach the steel, the larger will be this stage 1 time. Okay, and technically this is known as the corrosion initiation period, or we can say depassivation time. Okay, breaking of passive layer time. Okay, now once the corrosion has initiated, we have stage 2. Okay, which is known as propagation period, where corrosion starts to damage the concrete. And then once cracking happens, then there is a shoot in corrosion rate, which is defined as stage 3, which is known as acceleration, where there will be spalling and delamination of cover concrete and excessive cracking of cover concrete. Okay, so in the first figure you can see how concrete behaves in these different stages and how the cumulative damage grows. Okay, so before corrosion there is no damage, then once corrosion initiates we can see cracking is happening at the interface. This crack slowly grows till the cover, and then there is spalling and delamination of cover concrete. Okay, now if we relate this to the cost of repair cost, so we can say that the more we will delay the action against corrosion, the higher will be the cost incurred to repair the corrosion damage. Okay, so initially at the micro cracking stage, if we can detect corrosion, then the cost incurred will be lower. However, after spalling or delamination we try to address corrosion, then the budget of repair will also be significantly high. Okay, so the more earlier we are able to detect corrosion, the better it will be to address the issue. Now just try to answer these three simple questions, and in the meantime if anyone has any doubt regarding the basic definition of corrosion that we have discussed till now, you can ask. Hey, sorry, I guess somewhere in between the network went off. Can anyone tell me at what slide I was when the network went off? I was not able to check. What I was discussing when the network went off, can anyone tell me? Hello? Am I audible?
Yes, sir. Audible, audible.
On which slide I was when the network went off? Can you tell me? So we started with this definition part up till where we were able to discuss.
Slide number 10.
Okay, so I discussed about passivation, that there is a passive layer over the steel surface. Okay, and this passive layer shields against corrosion. Okay, due to the formation of this passive layer, the rate of corrosion inside reinforced concrete is very small. However, when aggressive ion ingress through the concrete, they can break the passive layer and they can initiate corrosion activity. And the aggressive ions which are responsible for this is CO2 and chlorides. Okay, so we have two forms of corrosion: carbonation induced corrosion and chloride induced corrosion. Okay, so till this point I have discussed, right? You were able to hear till this point?
Yes, yes.
Okay.
Yeah, yes. Up to this point.
Okay. So the next thing is, what's the end result of corrosion? Okay, so that is corrosion products, or what we generally call as rust. Okay, so the rust that is formed due to corrosion, it can have different composition based on the availability of oxygen and moisture. Okay, so we saw FeOH whole twice, that is iron 2 hydroxide. There can be iron 3 hydroxide which can form, or it can be ferric oxide, ferrous oxides that can form. It can be FeOH, goethite, ferrihydroxide oxide, oxyhydroxides. Okay, so there can be different types of rust product that can form based on the availability of oxygen and moisture in the vicinity of steel. Okay, on an average, these rust product, they occupy 4 to 6 times higher volume than the base steel. Okay, now inside concrete, we know we have a very confined space. Okay, there is no space for accommodating any expansive products. Okay, so when these when rusting happens over the steel reinforcement that is embedded inside concrete, they give rise to tensile stresses. Okay, and when these stresses exceeds the tensile strength of concrete, then cracking will happen in the cover concrete. Okay, the same thing you can see through different images. So you can see here longitudinal reinforcement and stirrups, they are heavily corroded, due to which the cover concretes fall. Okay, the same thing you can see here also, there where this falling of cover concrete due to corrosion of embedded reinforcement. The same thing on this wall also, you can see rusted reinforcement inside and spalling of cover outside. And this is an example of a steel infrastructure where you can see severe corrosion damage happened everywhere. Okay, so there are two things that are happening: either there will be delamination of cover, okay, which will expose the reinforcement directly outside, or there will be spalling of the corner concrete portions, okay, which will expose the reinforcement directly to the atmosphere. Okay, so if we look at this damage thing, from damage due to corrosion from a time scale point of view, so I hope I am connected here. So there is three stages in which we can define corrosion. Okay, so stage one is the time taken by the aggressive ions to reach the steel reinforcement. So we know we have a concrete, okay, and this is my steel rebar, and suppose there is a cover of say 50 mm. Okay, so we know that initially there is a passive layer which is formed over the steel surface, so there won't be any corrosion, or the rate of corrosion will be very small. Okay, and there are chloride ions in the atmosphere, so these ions, they will ingress through concrete over time. Okay, now once these ions will reach the steel surface, they will initiate the corrosion. Okay, so the time taken by these ions to reach the steel surface is known as the initiation period, or the depassivation time. That is the stage one of the corrosion cycle. Okay, now once the corrosion has initiated, we have stage two, which is known as propagation period. Okay, where the corrosion will start to damage the concrete. And then we have stage 3, which is known as acceleration period, where when cracking happens, there will be a shoot in corrosion rate. Okay, which will lead to failure of concrete in terms of spalling and delamination of concrete cover. Okay, so in this first figure, you can see how corrosion behaves in these different stages and how cumulative damage grows. So before corrosion, there is no damage at the interface. Then as corrosion grows, there will be cracking at the interface. These crack will grow till the cover surface, and then there will be smalling and delamination of the cover. Okay, so when we talk about repair against corrosion, the more delay we'll do again for repair, the higher will be the cost of the repair. Okay, so if we are able to detect corrosion when it is initiated, then the repair against corrosion will also cost less. However, if we think about repair at stage 4, when spalling and delamination has already occurred, then the budget demand for repair will also be very high. Okay, so it is important to address corrosion issues as early as possible. Okay, so now based on the understanding of definition of corrosion and breaking down that definition into different parts, just try to answer these three questions. And in the meantime, if you any one of you has any doubt regarding the content we have discussed till now, like maybe if you missed something due to network issue or something, you can ask. So these things right now we are focusing on very fundamentals related to corrosion. Okay, so just try to clarify as much as possible so that the things that we'll discuss ahead will be clear. Okay, first question says, what is the primary role of high pH environment in concrete regarding reinforcement corrosion? So can anyone tell me? So we know in concrete there is high alkalinity due to NaOH, KOH, and calcium hydroxide. Okay, so why this alkalinity? How this alkalinity play a role against reinforcement corrosion? Any guess for question number one? What will be the correct answer? So we have just discussed right now on slide number 10. So can anyone recall what was the reason for high pH? What is question number one? You are saying option one. No, it is not correct. It is incorrect. Okay, so the correct answer is option B. It passivates the steel surface, forming a protective oxide layer. So what happens in high pH? There is a protective layer that is formed over the steel surface, like we discussed here. Okay, now in this protective layer, it prevents further corrosion from happening, and that's why we use say reinforced concrete is compatible in nature, because concrete needs tensile strength, which reinforcement gives it to concrete, and reinforcement needs a medium which can protect it from corrosion, which is why which concrete gives to reinforcement because of its high pH. Okay, so in high pH there is a stable passive layer which is formed over the steel surface. Okay, and that passive layer, it prevents or it slows down the interaction of steel with environment, and that's why we say that reinforced concrete has an infinitely long lifespan until there is some aggressive ions which are coming at the interface, steel concrete interface. Okay, question number 2, which electrochemical reaction occurs at anode during steel reinforcement corrosion? So we, when I was discussing about kinetics of corrosion, I told you that there is oxidation and there is reduction. So what is happening at anode? So if you would have looked at the slide, it would have been clearer to you. Any guesses? Yeah, for first question, correct answer is B. Now for second question, what is the correct answer?
C. Answer C.
Yes, the correct answer is C. So when we talk about corrosion, it is not a single reaction. It is interaction of metal with its surrounding. So there are two electrodes that we say. One is anode and one is cathode. So at anode, what is happening? Iron is converting into iron oxide. And at cathode, what is happening? oxygen in the presence of moisture, it is consuming these electrons and it is reducing to OH minus. So this is my cathode. Okay, both anode and cathode, they are present on the same steel surface but at different location. Okay, so if I show this figuratively. So this is my steel surface. Suppose this is the site where Fe is converting into Fe2 plus. So what will happen? The electrons that is left behind, it will travel inside the steel surface to a different location, and at this location oxygen is coming in the presence of moisture and it is converting into OH minus ion. Once these two ions are formed, they combine together to form rust. Okay, so both reactions, or anodic reaction and cathodic reaction, both are happening on the same steel surface but at different locations. Okay, and anode is the point where we say oxidation occurs. Okay, now answer question number 3. Corrosion induced cracking in reinforced concrete typically follows which nature? What is the type of cracking we see due to corrosion? So if you have observed this on field, like when cracking appears in a concrete column or a beam due to corrosion, what is the nature of that crack? Any guesses? Yes, the nature of cracks are longitudinal cracks along the reinforcement. So whenever you see cracking due to reinforcement corrosion, you will see them appear as a longitudinal crack along the reinforcement. Like here am not able to show you clearly because both stirrups and longitudinal rebar are got corroded, but generally when corrosion occurs there will be a longitudinal crack along the reinforcement line, okay, which causes delamination of cover concrete. Okay, so this is kind of a representation of cracking due to corrosion. Like for shrinkage we saw there is map cracking, or when there is settlement, differential settlement, there is diagonal cracking. So for corrosion there is longitudinal cracking. Okay. Okay, so that was all about defining corrosion, like what is corrosion and how it occurs. Okay, now when we talk about degradation of steel reinforcement in concrete due to corrosion, we saw it can happen due to two reasons: chloride induced corrosion and carbonation induced corrosion. So this effect can be broadly said as direct effect and indirect effect. Okay, so direct effect means when steel itself get affected because of ingress of aggressive ions. So suppose this is my concrete and this is my steel reinforcement, and these are ions coming from the surrounding environment. So if these ions are directly affecting the steel reinforcement after ingressing through concrete, then we say that it is direct effect of ion. Okay, which is causing depassivation of steel surface, and these direct effect is caused by chloride ions. Okay, so what chloride ions do, they ingress through the cover concrete. They won't affect concrete. Okay, they are just directly affecting the steel reinforcement. So what they do, they ingress through the cover concrete, they break the passive layer and they interact with steel to form corrosion product. Like here chloride ions, it interacts with ferrous ion to form FeCl2, okay, which is a precipitate. Okay, in this way it is consuming iron. Okay, and then second is known as indirect effect, where when the concrete is affected due to aggressive ions, it causes depassivation of steel. So what are these ions? These ions, they are not causing damage to reinforcement, but they are causing damage to concrete, which in turn causes damage to reinforcement. So okay, what and which is this ion? That is carbonation corrosion. So what happens when CO2 moves through cover concrete? It affects the concrete cover. Okay, it decreases the pH of concrete. Okay, and once the pH of concrete is lowered than the passive layer, which is formed at high pH level, it starts to break, and due to which corrosion rate increases. Okay, so CO2, it is not directly interacting with steel, but it is interacting with concrete, and that is causing a corrosion rate of steel to increase. So that's why I say it is an indirect effect. Okay, and direct effects is due to chloride ions. So we'll move into these two discussions further in detail, but this was just a brief explanation of what is the difference between carbonation and chloride induced corrosion. Okay, so now let's see about carbonation induced corrosion in detail. Okay, so what happens is CO2, it diffuses through pores of concrete and it reacts with calcium hydroxide, and as a result alkalinity of pH is concrete is reduced, and this process is known as carbonation. So we have CO2 from atmosphere. So initially there is moisture inside concrete. So in the presence of moisture, CO2, it combines to form carbonic acid. Okay, so this H2CO3 is formed initially. Now this H2CO3, it will react with calcium hydroxide, which is present in the pore solution of concrete, to form CaCO3. Okay, now in this process what is happening? Calcium hydroxide is getting consumed. So as calcium hydroxide will get consumed, there the pH of concrete will lower down. Okay, so once the pH of concrete decreases, the passive layer that is formed over the steel reinforcement, it depletes, and that increases the rate of corrosion. But at the same time, CaCO3 is also forming, which is a solid precipitate. So that precipitate, it will fill the pores inside the concrete, which can lower the permeability also. So the carbonation induced corrosion has both the effect. It is decreasing the pH as well as it is filling lowering the permeability. Okay, so the rate at which carbonation induced corrosion is, that's why we say it is typically slow compared to chloride induced corrosion. Okay, because of this lower permeability that is occurring due to filling of pores. Okay, now when we talk about the end result, okay, so when suppose this is my concrete and this is my steel reinforcement, so pH, it will lower down layer by layer as CO2 will penetrate through concrete. Okay, so once this pH, which was over 12 at the interface, it becomes less than 10 or less than 8, what happens? The passive layer completely depletes. Okay, so corrosion that will happen, it will happen throughout the throughout the steel surface, and that's why I say that carbonation results in uniform corrosion. Okay, so uniformly across the steel surface corrosion is happening. Okay, once the pH is lower, pH decreases and passive layer depletes. Okay, so the electrochemical reaction that is happening, it is happening over the entire exposed surface or over the large area. Okay, large or throughout the exposed surface, the electrochemical reaction of corrosion is happening. Okay, so in such cases, what happens that the cracking that is occurring due to corrosion, it appears very fast at the surface. Okay, so that's why we say that the cracking due to carbonation induced corrosion, it can be detected at very early stages. Okay, so now, when we talk about cracking in concrete, as we have talked so much, it can be due to n number of reasons. It can be due to shrinkage, it can be due to creep, it can be due to fatigue. How we know whether it is due to carbonation, or if not cracking, how we know that up to how much depth this CO2 has penetrated inside, and after how many years the corrosion due to carbonation will initiate. So for this we use phenolphthalein indicator. Okay, so on this slide you can see, so these two images, you can see there is a concrete cross section that is broken from the middle, and there is a phenolphthalein indicator chemical that is sprayed over the concrete. So the indicator, it turns violet when the pH is more than 10. Okay, so this area in between where the color is violet, it means that this area has pH of more than 10, and this outside area has pH of less than 10. So in this way we can detect up till how much depth the carbonation has occurred. The same thing you can see here also. Okay, so using phenolphthalein indicator we get a idea of what is the degree of carbonation inside concrete. Now, naturally, this carbonation process is very slow. Okay, it can take up to 20 to 30 years for my concrete to carbonate up to this small depths of like 10 mm or 5 mm. Okay, So in laboratory, to study carbonation, we use accelerated carbonation chambers, okay, where we maintain conditions such that we can accelerate the carbonation rate inside concrete and we can compare the different concrete compositions in a short period of time. Now, what are these conditions under which carbonation accelerates? Disconnect. Okay, so in the figure, you can see the effect of relative humidity on carbonation rate. Okay, so uh, in the figure, so you can see that as the relative humidity is increasing, the rate of carbonation it also increases, and then after 80% or 70%, the rate of carbonation again decreases as the humidity increases. Why is that so? So if you remember the carbonation equations that we saw earlier, okay, these two equations, okay, so water is an essential part of carbonation, okay, because initially CO2 reacts with water to form carbonic acid, and that carbonic acid is what is reacted with calcium hydroxide to form CaCO3. Okay, so if my RH is lower than 40%, suppose say less than 40%, there won't be enough moisture for CO2 to react, okay, and if my RH is greater than 70%, then what will happen? CO2, which is a gas, it won't be able to diffuse inside concrete because diffusion of CO2 in water is very slow compared to diffusion of CO2 in air. So that's why we say between 50 to 70% or between 60 to 70%, the rate of carbonation is very high because there is enough moisture and there is enough air voids for CO2 to move and CO2 to react. Okay. So when we talk about carbonation depth modeling, like at what rate the carbonation is penetrating through concrete, so rate of carbonation it decreases with time. Why? Because CO2 must diffuse to the pores which are already carbonated. And we know that once carbonation happens, CaCO3 is formed which blocks the pores. So that's why rate of carbonation it decreases over time. Okay, so generally this penetration of CO2 over time it is represented by this equation, square root equation. Okay, so D is the depth of penetration of CO2 and T is the time. So it follows the exponent square root relation. So this will be like this. Okay, so over time the rate of penetration of CO2 it decreases. Okay, and K is the coefficient which defines the rate of diffusion, which is dependent upon CO2 concentration and the alkalinity of concrete. Okay, so this is how we define the carbonation rate through concrete. So if we know the depth of carbonation, then and if we know the value of K, we can detect how many years have been passed, or if we know the value of K and how much years have been passed to exposure, then we can also detect the depth of carbonation that would have occurred inside the concrete. Now, other factors which can affect the carbonation rate is the wetting drying cycles and the mineral admixtures which are present inside the concrete. So in the first figure, you can see the effect of wetting drying cycles. So more is the frequency of wetting and drying cycles, lower will be the carbonation rate. So you can see if we are exposing concrete to wetting drying cycles every once a week, the rate of carbonation is also very small because when the concrete is completely moist, CO2 ingress won't happen because CO2 is a gas and its rate of diffusion through water is very small. But if there is no wetting, then the rate of carbonation is also very high because CO2 has more easy pathway, has more easy access through concrete. Okay, and with SCMs, they have dual effect. Positive can be seen as they are densifying the pore structure when we add mineral admixture, so carbonation rate reduces. But the negative effect is when we talk about the SCMs, they react with CH to form CSH. So they are decreasing the pH of concrete before exposure of CO2. So if pH of concrete is lower, so when CO2 will move inside concrete, it won't have this barrier of CH, much barrier of CH. So CaCO3 formation won't happen much. So CO2 will have more path for ingressing through concrete. Okay, without any hindrance of CaCO3. Okay, so you can see in this figure, Portland cement is represented by this line. Okay, so Compared to Portland cement, addition of fly ash and GGBFS, they have increased the carbonation depth rather than decreasing the depth because of this consumption of CH, which is reducing the pH of concrete. Plus, it is uh, enabling CO2 to easily move through concrete without any barrier of CaCO3 formation. Although it decreases the pore solution density also, so this dual effect we can't see directly in one nature. It can happen in a positive or a negative way. Both are contradictory to each other. So here you can see in terms of proportion of adding also, like compared to 10%, 30% fly ash addition will cause more carbonation rather than 10%. Similarly, for slag also, higher is the proportion of OPC replacement by slag, the greater is the carbonation risk. Okay. Now, what can be done to protect against carbonation? So, since both moisture and air is necessary, a water saturated concrete will exhibit a very low carbonation rate. Okay, that is clear to us from this wetting drying discussion. Now, making a concrete denser will also reduce the carbonation rate. Like if we can have an impervious surface concrete, if we can do a coating over the concrete surface, that can lower the carbonation rate. Or if we use a very low W by C ratio, so we will have a very high strength of concrete and we'll have a very low porosity of concrete. So that can also reduce the carbonation rate. And finally, since pH drop at the reinforcement depth will initiate corrosion, having a higher cover depth can also increase the protection against carbonation. So if my cover depth is higher, the CO2 will be required to penetrate through a larger concrete depth. Okay, and that penetration will take much more time. Okay, so that can delay the corrosion due to carbonation. Okay, so these three are common ways in which we can protect a concrete against carbonation corrosion. Now, from your understanding about carbonation corrosion, just try to answer these three questions. And in the meantime, if you have any doubt regarding carbonation, you can ask. So, what will be the answer for question number 4? What is the typical critical pH threshold at which passive layer of steel reinforcement becomes unstable? Can anyone tell me? No, the correct answer is 9. Okay, so when carbonation lowers the pH of concrete from around 12.5 to below 9, the passive layer breaks down and the corrosion initiates. Okay, so that critical pH that we talk about for breaking of passive layer is around 9. So when it breaks down from 12.5 to 10, also the pH layer will start to become thinner. But at 9, it is the critical, it will break. Below 9, the passivation won't be stable anymore. Okay. Question number 5. Which environmental condition leads to fastest carbonation rate inside reinforced concrete? So I have given you four conditions. Okay. In which condition the rate of carbonation will be the highest? Any idea for question number? Okay. The correct answer is B. Okay, so we saw at moderate humidity there is enough moisture and enough air for CO2 to interact with moisture and form carbonic acid initially, and for CO2 to ingress also. Question number 6. A reinforced concrete beam has a depth of 40 mm. Okay, and it is exposed to carbonation. If the carbonation coefficient is given as 3 meter per year, after how many years the carbonation will reach 40 mm depth? Okay, so just try to solve this question. You know the equation. Okay, this is the equation. I have given you the carbonation coefficient and the depth up till which I want my concrete to carbonate. So how much time it will take? I'll just paste this equation here. So based on this equation, can anyone do the calculation? Yeah, I'll just tell you the answer. Okay, so this K coefficient is given to us, it is 3. Okay, and the depth of carbonation, it is the depth of cover is given as 40. Okay, so how many years it will take? Okay, so this T is what we need to calculate. Okay, so T will be nothing but 40 divided by 3 square. Okay, when we'll take under root out, so it will be square. So this it will come out to be around 178 years. Okay, so this is how long carbonation CO2 it will take to reach a cover depth of 40 mm if my carbonation coefficient is 3. And this carbonation coefficient, it depends upon the CO2 concentration at the surface, the diffusion rate of CO2 through concrete, and the alkalinity amount which is present in the pore solution. Okay, so based on that, this value can change. I hope everyone are clear with these three questions. Not 3.65. You might have done some mistake. Just see this equation and just give it one more try. If still you are confused, you can ask me. Okay, so this will be something 13.33. 13.33 square will be around 178 years. Okay, this is also in millimeter. This is also in millimeter. So whatever we are getting, we will get in years. Okay. Now, so now the next thing in reinforcement corrosion is chloride induced corrosion. Now these chloride based corrosion in concrete, it is a very frequent cause of corrosion issues, especially in structures which are present near the shoreline, like in Mumbai environment, Mumbai exposure environment. But from where these chloride ions are coming? So chloride ions, the source of chloride ions can be seawater, it can be soil or groundwater, it can be de-icing salt. Okay, so generally in cold weathers, when we want to remove ice from the surface of roads and all, so we spray de-icing salts. So those salts also are source of chloride ions. Then there can be contamination in cement, aggregate, and mixing water, which all can be a source of chloride ions. Okay, so if we see the transport of chloride ions through concrete for corrosion, this transport is a basic, it is a two-step process: initiation and propagation. So first step is the initiation, and by initiation we mean the time or a period up till which a certain amount of chloride ion will reach the steel surface. Okay, so that we have already seen. And then that there is propagation periods where the cracking will grow due to corrosion. Okay, now we say that certain amount of chloride ions will reach the steel surface, and that certain amount of chloride ions is known as chloride threshold. So why there is this certain amount? Okay, and what is this certain amount? So basically there is a passive layer initially over the steel surface. Okay, now this passive layer won't just break once chloride will reach the surface. Okay, it is not like suppose 0.1% of chloride it reaches the surface, so passive layer will break. No, it won't happen like that until there is a certain critical threshold of chloride at this interface. Once the chloride reached this interface in a certain critical threshold, only at that point the passive layer breaks. Okay, so and this value of threshold it depends upon two things: the reinforcement material and the pH of concrete. If the pH of concrete is lower, the passive layer will be thinner, so this threshold value will be smaller. And if my reinforcement, again, if it is coated rebar, then this threshold value will be different. If it is alloyed steel reinforcement, then this chloride threshold value can be different. Okay, so there is a threshold value in which chlorides needs to reach the steel surface to break the passive layer. Okay, so this movement of chloride through concrete, it happens via process of diffusion. Okay, so basically it is based on concentration gradient. So outside concrete there is a high concentration of chlorides, and inside concrete there is very low concentration of chlorides. So what will happen, chlorides will diffuse from higher concentration to lower concentration, and this process is known as diffusion. Okay, so the rate at which chloride is diffusing is one parameter that governs the ingress of chloride ions. The depth of concrete cover is one more parameter which governs the ingress of chloride ions, and the amount of chlorides which is present at the surface of concrete is also a parameter which governs the ingress of chloride ions. So if we see the zoomed in image also, initiation period, it is dependent upon four entities. First is the surface chloride concentration, which depends upon the exposure condition. Then the critical chloride threshold, which is a property of steel concrete interface. Third is the cover depth, okay, which is a design parameter. And fourth is the ion diffusion coefficient, which can be determined for concrete experimentally. Okay, so now the cover depth, the surface concentration of chloride, and this critical chloride threshold value we can already know. Okay, or we can know during the design or from the past experimental results of, like, suppose we have a sandblasted thermomechanically treated steel reinforcement, then for it and for such bar the C's critical threshold will be a fixed value. Then surface chloride concentration we can know from based on the exposure condition, and ionic diffusion and this cover depth we can know from the design parameter. But thing that we don't know about is the chloride diffusion coefficient, which can vary based from one concrete to another concrete. Okay, so for estimating this diffusion parameter, the chloride diffusion coefficient, the ingress of chlorides through concrete, we model it using fixed second law of diffusion. Okay, so this fixed law of diffusion, it helps us to uh, model how chloride ions are moving through concrete. Okay, so the basic fixed law, it is written like this. So del C by del T is equal to dCl of del 2C by del X square. Okay, so del C by del T defines the rate at which chloride ions are penetrating over time, and del 2C by del X square defines the spatial distribution of chloride ions over depth. Okay, so this equation, it is known as the fixed second law of diffusion. Fixed second law of diffusion. Now this is a differential equation. So to solve this differential equation, we need some boundary conditions, so that which we can assume to solve this equation. So the two boundary conditions that we assume is, we assume that concrete is a semi-infinite homogeneous medium. So semi-infinite means we know a certain covered depth of concrete is there, and on the other side there is an infinite exposure environment. Okay, there is no limit for the exposure of concrete. Okay, so that's why I say it is a semi-infinite homogeneous medium. We assume concrete as a homogeneous material, so chlorides are moving from this infinity environment to this finite space. So at x is equal to 0, which is the surface, the chloride concentration is Cs, and at this x is equal to d, which is the covered depth of concrete, the chloride concentration is Ci or maybe 0. It depends upon the quality of cement and water we are using. So chloride ions are moving from the Cs point to Ci point, from x is equal to 0 to x is equal to D. So these are our boundary conditions. So knowing these boundary conditions, we can solve this equation and we'll get this end equation. Okay, which will help us to relate the time it will take for chloride ions to move from this covered depth of D, or we can say X, knowing the surface chloride concentration, the initial chloride concentration in concrete, and the critical threshold. Okay, so based on this, we can estimate the DCl coefficient also by experimentally determining in lab. Okay, so how this is done in lab? Okay, so for this we have a testing which is known as bulk diffusion testing, which is as per ASTM C1556 guidelines. So in this, what we do, so here we take a concrete cylinder, okay, and we coat the concrete cylinder on the curvature side. Okay, so this is my face which is exposed, okay, which is not covered by epoxy. So epoxy is like a thin layer, a barrier which will prevent the interaction of water with concrete. Okay, so when we keep this concrete in the chloride solution, what will happen? Through this uncoated surface, the chloride will move inside. Okay, now after a certain exposure period of say 35 days or 40 days to this chloride ponding solution, we'll take the concrete sample out and we'll correct concrete powder from different depths. Okay, let's say 5 mm, 10 mm, 15 mm, 20 mm. Okay, once we collect those concrete powder from different depth, we'll estimate the chloride concentration in this powder and we'll form this profile. Okay, which is chloride content versus depth profile. And this, on this profile, when we'll fit this fixed equation, we'll get the DCl value. How? Because we know the surface chloride concentration, we know the initial chloride concentration, we know the X value, and we know the T value. T is the time till which we have kept our sample for exposure in chloride solution. So knowing all these values, we can determine the chloride ion diffusion coefficient. Okay, so this is how we determine diffusion coefficient in lab. And we can also check in this way how this value will evolve over time if we increase the ponding period. Okay, so how concrete can influence the DCl value? Okay, so it depends upon the permeability of concrete. If I have a denser concrete, suppose I have a M55 grade concrete and I have a M25 grade concrete. So M55 grade concrete is denser in nature. So rate of chloride ingress through this concrete will be lower. So the diffusion coefficient of chloride ions in a M55 grade concrete will be smaller compared to a M25 grade concrete. And it also depends upon the chloride binding ability. So what happens? CSH, C3, calcium alumina hydrate phases, all they have the ability to absorb chloride ions also. So as chloride ions move through concrete, they can block these ions also. So that is known as chloride binding. So depending upon the amount of CSH and CH phases inside concrete, it can also affect the diffusion of chlorides through concrete. So generally we say that a GGBFS based concrete, which is rich in aluminates, it has a higher chloride binding ability compared to a OPC based concrete. So such concrete, it may show lower diffusion coefficient compared to a OPC based concrete. So this figure shows some of the experimental data of mine for different binder composition and how the DCl value, the chloride ion diffusion coefficient value, is evolving over time. So this, I did this testing, this bulk diffusion testing on different ages. So I kept it under chloride exposure for 20 days, then 90 days, and up till 365 days also. So you can see as the exposure age increases, as the concrete densifies over time, the rate of chloride diffusion is also decreasing.
Sorry, your
Okay.
screen not visible.
It is visible.
Ah, now it's visible.
It may be some network fluctuation which causes this issue. Is it, was it visible till slide number 23?
Yeah, 23 visible and
Okay.
24 4 only in the beginning.
Yeah, your voice is also breaking, so it can be some issue at your end also or my end also. If everyone is facing this issue of screen not visible, then it may be my end, or if it is at your point only, then it can be your issue, network issue also. But anyhow, you can tell me. I will repeat the part whenever this happens. Okay. So what I am saying here is that as we increase the exposure period, we can see that the diffusion coefficient is dropping in all the cases. Why? Because concrete is densifying as the hydration age is growing. So that is slowing down the ingress of chloride ions. यहाँ पर आवाज मत कर. Okay, and we can see the effect of SCMs also. So you can see this is the OPC based concrete line. Compared to OPC based concrete, initially the slag system was showing a very high diffusion coefficient value because pozzolanic reaction is slow in nature. However, after 365 days, you can see there is a significant decrease in diffusion coefficient in a SCM based concrete compared to a normal OPC concrete. Okay, so this is OPC 100. This is second case is when 25% fly ash replaces OPC. Then third case is when 40% of OPC is replaced by slag. In the fourth case, 8% of silica fume replaced OPC. And the similarly for ultrafine slag and ultrafine fly ash, I generated the data. Okay, so in this way, you can understand the effect of concrete property over the diffusion coefficient value. Now, another quick way in which we can check the concrete durability against chloride ingress is through rapid chloride migration testing, which is done as per NT-Build 492 guidelines. Okay, so RCMT, it is a electrically accelerated test method which is used to determine the chloride ion diffusion coefficient to concrete. And this testing is based on Nernst-Einstein theory of migration, in which chloride ions, they are forced to migrate through concrete through potential difference which is induced by a DC power supply. So basically what happens, chloride diffusion testing that we saw just right now, it takes almost 35 to 40 days to give us some result. However, on site, sometimes when we prepare a trial concrete, we need the judgment of durability very quickly. And in such cases, we can use an RCMT, rapid chloride migration testing, instead of a bulk diffusion testing. So in the figure, you can see the setup of an RCMT. Okay, so what we do, we take a 100 cross through 100 cylinder, concrete cylinder. From this concrete cylinder, from the middle portion, we cut a 50 mm concrete disc. Okay, so this concrete sample will be 50 mm wide and 100 mm in dia. Okay, so this is what you see here. So this concrete sample, it is placed between two electrode. One electrode is here and another electrode is at the top. Okay, at the top, okay, this is a complete beaker. Okay, and this is an electrode place over it. So here I am filling the NaOH solution. Okay, and at this bigger jar outside, I am filling the NaCl solution. Okay, so this electrode at the bottom, we connected it to the negative terminal of DC supply, and the top one we are connecting to the positive terminal. Why? Because chloride ions are negatively charged. Okay, so what we will do, when we'll apply some potential difference, when we'll make this surface positive, chloride ions, it will try to move through concrete from negative terminal to positive terminal. And this movement of chloride ions in the influence of potential difference is what is known as migration. Okay, so we are accelerating the movement of chloride ions through concrete. Then after a certain time, say 24 hours, we'll break the concrete and we'll check the penetration depth of chloride ions. And then there is a formula that is given in NT-Build 492 code, using which we can estimate the DSNSM. Okay, so non-steady state migration coefficient of chlorides. Okay, so this diffusion value, this migration coefficient of chloride we estimate. So this testing is generally done for site examination if we want to compare a M55 grade to a M40 grade, or we want to check the quality of concrete that we prepared in laboratory and how it is getting affected on site. A quick way to check is RCMT testing. Okay, against chloride ingress if you want to check the concrete quality. Okay, now based on your understanding about chloride corrosion, just try to answer these three questions. And in the meantime, if anyone has any doubt, you can ask. So question number 7 says, which type of corrosion is most associated with chloride induced damage in reinforced concrete? So what type of corrosion will occur on the steel surface? Whether it will be a uniform corrosion or a localized corrosion.
So pitting corrosion.
Yes, the correct answer is pitting corrosion. Why? Because when we talk about this ingress of chloride ions through concrete, it won't happen uniformly across the concrete. Okay, so what is happening here? So we have this concrete, okay, and chloride ions are moving through the pores that are present inside the concrete. Now the connectivity of pore will depend the path of chloride ions. So they may move in a random orientation manner and they will reach the reinforcement surface at a particular location. Now only when this chloride ion will reach this value above critical chloride threshold, it will initiate the corrosion. So such things happen locally. So at this point, suppose chloride has breached this CTL value. Okay. So here only the corrosion will initiate. The rest of the site will act as a cathode. Okay. And this location will act as a anode. So the corrosion will grow locally here. Okay, so that's why we say it is a pitting corrosion. A pit is forming. Okay, like this, a pit will form where rebar is degrading at the same site until there is chlorides which breaches everywhere uniformly. Until chlorides breaches everywhere uniformly, the pit will continue to grow at a specific location. And this pitting is can be also be said as a localized loss of steel reinforcement. Question number 8. Which type of cement is most effective in reducing chloride penetration in reinforced concrete? Can anyone tell me? No, the correct answer is PPC with fly ash. So we have seen that when we add supplementary cementitious material, they will densify the concrete. Okay, once they will densify the concrete, the ingress of chloride ions it will slow down. So you can see in this diagram how I explained. Okay, so a fly ash based concrete system has a lower diffusion coefficient diffusion coefficient for chloride ions compared to a OPC based concrete because it has lower permeability and it has more CSH formation which can bind the chloride ions also later on. Okay. Question number 9. Why does the combined effect of CO2 plus chloride attack significantly accelerate the reinforcement corrosion? So can anyone tell me, suppose both CO2 exposure is also severe and chloride exposure is also severe. So why in such condition the reinforcement corrosion is getting accelerated? Although one is indirect and one is direct effect, how they both are clubbing together? Any guess for question number 9? Yes, the correct answer is P. So what is happening? Carbonation, it reduces the pH of concrete. Once the pH of concrete reduces, the passive layers becomes thinner, and as the passive layer is will become thin, the critical chloride threshold will also decrease. So at a smaller quantity of chloride ions itself, the corrosion can initiate at the steel surface. So this is how combined effect of carbonation and chloride can significantly accelerate reinforcement corrosion. Okay. So now to understand corrosion better, as we saw in the definition of corrosion, it is important to understand the thermodynamics and kinetics of corrosion from a technical point of view. So today we'll discuss about thermodynamics of corrosion, or we can say electrochemistry behind corrosion. Okay, so what do we mean by electrochemistry? Okay, so electrochemistry means that chemical reaction or a group of chemical reaction which involves electron movement. Okay, like corrosion, it is an interaction of metal with its surrounding, and it is an electrochemical reaction which is happening at the steel surface. By surface, we mean that the interaction is happening at the metal non-metal interface. So this is my steel, which is a metal, and this is my surrounding, which is a non-metal. Okay, so this electrochemical reaction is happening at the surface of the metal. Okay, and there is electron movement that is involved, that we saw in the anodic and the cathodic reaction. So electrons are produced and these electrons are getting consumed, so that's why it is electrochemistry. Okay, electron movement is happening in a group of chemical reactions. Okay, so if we represent this corrosion reaction in the simplest of manner, we can write this equation. There are two reactant products A and B which are converting into final products C and D. Okay, so here A represents the metal, B represents the non-metal. So A can be Fe, B can be oxygen in the presence of moisture. Okay. So C and D are the reaction products. So one will be Fe2 plus and the other one will be OH minus in case of corrosion. Okay. So A is getting oxidized uh, and B is getting reduced. Okay, so M is converting into M plus, so Fe is converting into Fe2 plus, and and O2 is converting into OH minus, so it is reducing. So one is oxidation and then the other one is reduction. So we say corrosion is a electrochemical reaction, oxidation reaction which occurs at anode and really results in release of electron like you saw here, and reduction reaction which occurs at cathode which consumes the electron released by the anodic reaction, which is this reaction. Okay, so this is how we define the electrochemistry behind corrosion. Now, when we look at these oxidation and reduction reactions, these reactions are charge transfer processes that are occurring at the interface of a metal and an aqueous solution. Okay, and hence they will depend upon the potential that essentially corresponds to electrode potential of a metal. Okay, to understand the statement, you need to see the figure. So in the first figure, you can see iron is converting into iron 2 plus. It is leaving behind some electrons, which is moving from one location to another location. And these electrons, they will move inside the concrete, and oxygen from the non-metallic environment, uh, it will consume the electrons to produce OH minus ions. Now, in the environment where there is both OH minus ions and Fe2 plus ions, they will react to form what is known as rust. So, inside metal, electron movement is happening, and outside metal, charge movement is happening. Now, for these movement to occur, there should be some potential difference. Then only charged species can move from one point to another point. So we know negative charge, it will move from towards positive direction, and a positive charge will move towards negative. Okay, so negative charge, it will move from lower potential to higher potential, and positive charge, it will move from higher potential to lower potential. So there should be some potential difference, then only the charged species can move from one point to another point. So for this, if you see the second figure, between the two sides, so this is my one side and this is my second side, electron inside is moving from negative to positive, while positive ions outside, it is moving from positive to negative. So this Fe is moving here and these electrons are moving here. So Fe is moving from positive to negative, electrons will be moving from negative to positive. Okay, so positive represents higher potential, negative represents lower potential. So if we compare the potentials inside and outside, so at this anodic side we can say the potential inside is lower than the potential outside. Okay, inside concrete, if we say that inside steel, if we say that this potential here it is lower than this potential here. Okay, and outside the steel surface we know potential at this position is greater than potential at this position because from the movement of ions. Okay, so if we subtract these two equations, okay, equation 1 and equation 2 will get the potential difference at this location compared to potential difference at this location, and this is known as electrode potential. Okay, the final equation that we get here is known as the electrode potential. Now, measuring this absolute value of potential at a steel surface, it is not possible. Okay, we can never measure the absolute potential of a material. So for recording potential, we report it with respect to a certain electrode, standard electrode system, okay, whose value we know. And one such system which is most standard is the standard hydrogen electrode. Okay, so the standard hydrogen electrode represented by SHE is electrode that scientists use as a reference for all half cell potential reactions. Okay, so this is one kind of a half cell, Fe converting into Fe2 plus and releasing two electrons. Okay, so this is one half cell. Okay, now what is the potential of this reaction? We can't know. So for this, we need a standard reference electrode whose potential value we know. And one such standard electrode is standard hydrogen electrode. Okay, so you can see in this figure how this electrode is made. Okay, so this is composed of 1 molar of hydrogen ion, okay, which is the hydrogen ion solution containing one square piece of platinized platinum, okay, inside a tube. So there is a tube inside which we have 1 molar concentration of H plus ion with the platinum rod. Okay, and during the reaction what happens, hydrogen gas is passed through it. Okay, so H plus ion it converts into H2 gas. Okay, and the potential for this reaction is 0 volt. Okay, so this is kind of a reference that we use for all other reaction. Okay, so if we have, if one half cell is this, Fe is converting into Fe2 plus, so this is my anode. Okay, if I make this reaction as my cathode, then I can know the potential of my anode. Okay, so with respect to cathode I can know the potential value of my anode. So that's why this is known as a standard electrode potential. Okay, there are other standard systems also like CuCuSO4, HgHgCl2, AgAgCl. These are all standard potential cells, okay, whose value we can determine as an absolute manner. Okay, so in the table you can see with respect to standard hydrogen electrode whose potential is 0, what is the value of different half cell reactions. So you can see Fe2 plus converting into Fe has a potential of minus 0.44 volt. Okay, similarly for all other metals we can estimate the potential of electrode potential if we know a reference value. Now, these electrode potential that we saw, they have two things to note about. First, they are half cell reactions and not complete reactions. So we estimated potential for a half cell, but we know corrosion is not just one reaction, it is both anode and cathode. Okay, which is a combined, which combines gives a complete cell. And second is that it is only for a half cell. Okay, this is the first limitation. Second is the potential value. It is that we have determined here, it is for certain standard conditions like 1 molar concentration of ions and for a fixed temperature. In reality the conditions, this type of condition may not be true. Okay, so to calculate electrode potential in any condition we use Nernst equation. So what Nernst equation says, Nernst equation is the equation that relates the capacity of an ion to take up one or more electrons measured in any condition to that measured in standard condition. So in standard condition, we know the potential value that is given by this table, okay, which we generated based on standard hydrogen electrode. For any condition, if we want to know the electrode potential value, we'll use the Nernst equation. And how it calculates the value? So this is the reaction equation that is there. Okay, so a reduction potential in any condition is equal to reduction potential in standard condition minus 2.30 T RT upon NF log the activity factor of product upon the activity factor of reactant. So this T is the temperature of the in which the reaction is occurring. F is the Faraday's constant, that is 96500 coulomb. R is the gas rate constant, and N is the charge number of electrons involved in the reaction. So here it is N number of electron. M to the power n is the concentration of product, and Mn plus is the concentration of reactant. Okay, so how this reaction came? It came from this want Hoff isotherm. So we know the Gibbs free energy, it is represented by this equation, and delta G it is equal to minus NFE. Okay, so when we say that when delta G, the Gibbs free energy is negative, we say that the reaction is spontaneous. And if this delta G value is greater than 0, then we say reaction is non-spontaneous. And for corrosion, delta G is less than 0 because it is a spontaneous reaction, it is bound to occur. Okay, so and this is the Nernst equation that is derived. Okay, so in any condition we can estimate the potential of a system. Like if we write the Nernst equation for a standard hydrogen electrode here, so we know what is the reaction. Okay, H plus ions, it is consuming one electron and it is converting into hydrogen ion, hydrogen atom. Okay, so if I write the Nernst equation for this hydrogen gas, it is converting into hydrogen gas, so half mole of H2. Okay, so if I write the Nernst equation for this equation, so E reduction for H plus to convert into H2 will be given by E naught reduction. So standard reduction potential for H plus to convert into H2, okay, minus 2.30 T RT upon NF log M of what is the product that we have H2, concentration of H2 upon concentration of H plus ion. Okay, so this is how we can write the Nernst equation. Now we know here we have taken the pressure of H2 is 1 bar, the concentration of H plus ion is 1 molar. So this log value will be equal to, this inside value will be equal to 1, and log of 1 is equal to 0. Okay, so this equation it will come down to, this part will become 0, so it will be electrode potential of this reaction in any condition will be equal to the standard electrode potential of H plus converting into H2, and that is 0 as we know from this table. Okay, this reaction has the absolute potential value of 0. So you can see that in any condition, in any temperature condition, the value of the standard electrode doesn't change, and that's why this hydrogen ion system is used as a standard electrode potential. Okay, now for any general electrochemical reaction, if I want to write the Nernst equations, I have a product A which is converting into B, and H plus ion it is converting into H2. So my electrode potential equation, it will be nothing but oxidation of A minus oxidation of B. Okay, so this is my anode and this is my cathode. Okay, so oxidation of A minus oxidation of C, or I can write as oxidation at anode plus reduction at cathode. So that will define my net electrode potential, and for both the cells we can write the Nernst equation based on the quantity of product and the quantity of reactant. Okay, so this is how we can write Nernst equation for any condition. Okay, for any combination of reactant anode and cathode species, we can write the Nernst equation and we can estimate the electrode potential knowing the standard electrode potential value. Now, what is the application of this Nernst equation? So, in reality, it is not just like one equation is occurring at the surface. So, when we talk about steel surface, also iron, and it is exposed to environment, suppose which has O2 and H2O. It is not just like iron is converting into iron 2 plus. No, iron 2 plus can also convert into iron 3 plus. Then iron 2 plus can also interact with O2. Iron 3 plus can also interact with O2. The formed iron hydroxides, they can also react further to form iron oxide. So there can be multiple oxidation and reduction reactions that can happen. Now there are, and now what reaction will happen, it will be depending upon the potential and the pH of the system, and this is represented by pore based diagram. Okay, so Pourby's diagram, it is a map which shows the most stable species in the solution as a function of pH and voltage. So when we know under a certain voltage and pH which reaction will be happening, that is known to us by pore base diagram. Like you see here the pore base diagram for nickel. Okay, so there can be three possibilities of reaction: nickel converting into nickel ion reacting with water to form hydroxide, or nickel directly reacting with moisture to form nickel hydroxide. So all these three reactions are possible. So if we write Nernst equation for all the three reactions, and if we plot it on a pH versus potential scale, so we'll get different stability zones for different material. Okay, so at a potential value lower than point minus point 0.2, nickel is stable. At a potential value higher than this point, nickel ion is stable, and at a higher pH of above 6, NiOH whole twice is stable. So, depending upon this, we can know which form of product will exist in which condition. Okay. Similarly, there is application for in iron also, which becomes a little more complicated because there are more possibilities of reaction to occur. So the same pore-based diagram using Nernst equation we can make for iron also by writing Nernst equation for all combination of reactions. Okay. So when we write Nernst equation for all these reactions and you plot the E value versus pH value. Okay, so in Nernst equation you get final relationship like this. Okay, so as you vary pH, the E value will also vary. So when you make this plot of E versus pH for all these reactions, you will get a pore base diagram like this. And in this again you can define the areas where the steel will be stable, or steel will be corroding, or steel will be in passive state. Okay, so ultimately what pore base diagrams tells, it tells the stability of corrosion reaction, or it can tell us the probability whether the corrosion will occur in a certain pH or potential system or not. Okay, so this is the application of pore base diagram. Now how these lines are formed, just give it a try. Okay, you know the Nernst equation, you know all the equations I have mentioned here. Okay, for all these lines I have mentioned the equations. Okay, which line is governed by which equation. So for all these equations, just give it a try. So try to write this equation. Okay, and just once you will write the equation, you will get an idea, okay, how the lines are coming up. Okay, so from the Nernst equation solution we get the pore base diagram, and from pore base diagram we can tell about the possibility of corrosion to occur or not in a certain pH and potential environment. Okay, and this is the ultimate use of thermodynamics of corrosion. We estimate the potential and we get the possibility of reaction to occur or not. So this is thermodynamics of corrosion. Now, based on your understanding about this part, just try to answer this simple question. And if you have any doubt right now regarding Nernst equation or pore-based diagram, you can ask. Please feel free to ask any doubts that you have. Okay, the more you will ask, the better clarity you will get. If you have no doubt, then try to answer these questions. So by answering the questions also, you will get better clarity about the concept. Okay, so question number 10 is, which of the following factor does not affect the electrode potential of a half cell? So I will paste this equation here so that you can think through equation. So this is a Nernst equation that for which we used to write electrode potential of for a half cell. Okay. So which factor won't affect this potential value? Any guesses? Yes, the correct answer is D. So you can see in the equation, the electrode potential, it depends upon temperature, it depends upon the concentration of ions in solution. Instead of concentration, it can depend upon the gas pressure also if it is gas. Okay, but it is not dependent upon the molar mass. Okay, this is concentration and not molar mass. So anywhere in the equation we don't see molar mass coming into picture. Okay. Question number 11. Which of the following is true regarding spontaneous electrochemical reaction? Okay. So you know how Gibbs free energy coefficient is related to electrode potential. So based on this equation, can anyone tell me for a spontaneous reaction what should be the condition? So we say corrosion is a spontaneous reaction. It is bound to occur. So for corrosion reaction, what should be E and what should be delta G? Any guess for question number 11? Okay, correct answer will be B. Sorry, D. C. C. So we say that for a spontaneous reaction, delta G should be less than zero. Okay, that is the Gibbs free energy. When delta G is less than zero, we say that the reaction is spontaneous in nature. So if delta G should be to be less than zero, E should be positive because it is negative of NFE. So if E is greater than zero, then delta G will be less than zero. So that's why correct answer is C. So for a spontaneous electrochemical reaction, the E cell value, the electrode potential should be greater than zero and delta G value should be less than zero. Question number 12. So I have given you a Nernst equation. So this factor that you see 0.0059, it is nothing but 2.030 T RT upon F. So when temperature is 298 Kelvin, this will reduce to 0.0059 because F and R are constant. This is gas constant and this is Coulomb's constant. So their value are fixed. Okay, so that's why we alternatively write Nernst equation as minus 0.0059 upon m. Okay, so for this equation that is given for a half cell, when E will be equal to E naught. Okay, under what condition E will be equal to E naught? Can anyone tell me? So just see this equation and think what can be the answer. So for E is equal to E naught, this value should be equal to 0. And log of 1, we know it is equal to 0. So when molar concentration of the reactant will be equal to 1, then we can say that E will be equal to E naught. And that is the condition that is there in standard hydrogen electrode. Okay, so H plus ion concentration is 1 and H2 gas pressure is also 1 bar. So in that condition, the second terms becomes 0. So E is equal to E naught, and E naught value for hydrogen electrode, hydrogen half cell, is already 0. So that's why we say it is a standard electrode for any temperature. Okay, so correct answer is B. Now try to answer these three more questions. So these are related to pore base diagram. Okay, so it will clarify your understanding about pore base diagram. So question number 13, what does pore base diagram primarily represent? Okay, so what we are understanding from pore base diagram, can anyone tell me? Any guess for question number 13? Just think what we're discussing in pore base diagram. It is a representation of potential versus pH. Okay, so what we understand from the plot, like this plot that we saw here, what we are understanding from this diagram. So basically, we are understanding stability of different oxidation state of an element. Okay, so this is what we are getting from pore base diagram. Okay, so you see at a pH value of up to 7 and a potential value of lower than minus 0.05, we say Fe is the stable state. At greater at as the pH potential increases, we say Fe won't be the stable state. Fe2 plus will be the stable state, or Fe2O3 will be the stable state. So depending upon the potential and the pH, we can estimate the stability. We can predict which oxidation state of a metal will be stable, and that is what we are using pore base diagram for. Okay. Question number 14. In the pore base diagram, which of the following conditions typically indicates a region where metal is thermodynamically stable but it won't corrode? So, which region generally presents metal is stable but it won't corrode? So, if I show you pore base diagram for iron, so which region is telling this? So, this is pore base diagram for iron, this is pore base diagram for nickel. So can you find any similarity in both the pore base diagram? What region is telling that the metal is thermodynamically stable and it won't corrode? Okay, so the region where metal is it in its elemental form, like iron is present in the form of Fe, or nickel is present in Ni state and not Ni2 plus, or not in any hydroxide state, that state is the region where metal is in thermodynamically stable and it won't corrode. Okay, so in its stable metal state we say that a material won't corrode, and this thermodynamically stable state we have seen in earlier discussion also. Okay, last question: which of the following statement is true regarding pore base diagram for iron? Okay, so if I show you the pore base diagram for iron again, which statement is true? Can anyone tell me? Okay, correct answer will be C. Okay, so at low pH region, if you see here in this Fourier diagram, okay, so at low pH region, you can see uh, iron forms Fe2 plus and Fe3 plus. Okay, when potential is higher than minus zero point 0.5 volt in low pH region, it typically forms Fe2 plus and Fe3 plus. Okay, which leads to corrosion. So these are corroding states, which is marked in red. Okay, and that typically exists in low pH regions. Okay, so in this way we can have a prediction, okay, which state will be stable in which pH condition or which potential condition. But this is still talking about possibility, it is not talking about the rate at which the conversion is happening, and that depends upon kinetics of corrosion, which we'll discuss in the next session. Okay, so for today's session, we had discussion about carbonation and chloride induced corrosion, and then we discussed about science behind corrosion. We discussed electrochemistry of corrosion, and we discussed about electrode potential from Nernst equation and pore base diagram. Okay, this was all for today. Thank you. So next week we will having one extra session also, that will be on